This video is part 2 of section 9.8, talking about power series. In the previous video, we introduced power series and then talked about the radius of convergence of a power series. Now we're going to take it a little step further, and we're going to talk about the interval of convergence of a power series. So the interval of convergence, if the radius of convergence is a finite number, each endpoint must be tested. That is huge. Okay, so if you have the finite number radius of convergence, then you have to test each endpoint. If you get a convergence of 0 or a radius of convergence of infinity, then you do not have to do that. So let's see how this looks. So in number 4, we want to find the interval of convergence of the series x to the nth over n. Now notice that I've already done for you the ratio test. Okay, so that's the ratio test. So if we were to apply the ratio test just like we did in the last video, we would have gotten our limit to equal the absolute value of x. Okay, so what that means is when you get a limit that still is involving x, then you have to govern where x is going to be in order for that to be less than 1. All right, so I'm just going to pick it up as if we had already done that. All right, so since our limit is absolute value of x, to converge, we want the absolute value of x to be less than 1. Or in other words, we want x to be between -1 and 1. Now, in the last video, we were just talking about the radius of convergence. So for this, radius of convergence would be 1. Centers at 0. We go from -1 to 1. Radius of convergence is 1. Now, the interval of convergence, however, is not what I've written here in green, okay? Because at -1 and 1, I actually don't know whether the series is converging or diverging, okay? So I actually have to test those two values for x to see if the series actually converges or diverges. And this goes back to all those tests that we learned in the first part of chapter 9. So what I mean by that is I'm going to test at x equals -1. So test at x equals -1. So that means I'm going to take my series, and remember my power series is a function of x. So as x changes, the series changes. And so those series are going to only converge for certain values of x and diverge for certain values of x. So I need to actually find out what's happening at -1 and 1. And this is where that inconclusive piece with the ratio test came in. Because if x equals 1 or -1, then remember the ratio test said that's inconclusive. Well, now we can actually see now we can actually conclude for -1 and 1. All right, so what that means, I'm going to take x equals -1, and I'm going to plug it in for x here in our series. So we have the series from 1 to infinity of -1 to the nth over n. And now you see that x is not there anymore, and so this is just like what we did the first half of this chapter. So -1 to the n over n, I want you to be able to easily recognize that as that's harmonic, alternating. So this is the alternating harmonic series. And you need to know and memorize that that series is always going to be convergent. Okay? And you don't even have to prove it. You just have to recognize it's alternating harmonic and state that it converges. So what that means is at the point x equals -1, while ratio test was inconclusive, when I plug in -1, it shows that we're actually convergent at -1. So how that would change my interval of convergence is that instead of being x is bigger than -1, it's actually -1 is less than or equal to x. Okay? So that's how that testing those endpoints works. So now we also need to test at x equals 1. Now, when you're doing this on the AP test, or on one of my tests or quizzes, you cannot just simply do this in your head. You have to show that you're testing the endpoints. If you don't show this work that I'm showing over here in the red and the blue, then you would not receive credit. All right, so testing when x is 1, you have the series x to the n, so 1 to the nth. 1 to the nth is just 1 over n. And now you see, hopefully, that this is harmonic, not alternating, therefore diverges. So at 1, at +1, our series doesn't converge, but at -1 it does. So then the interval of convergence, I already have it written, but I like to write it again sometimes and label it as the interval of convergence. And you can use actually interval notation here. So the bracket for -1, and then at 1, the parentheses. Okay, so that's how we do interval of convergence. So when you do ratio test, and you have a finite number as your radius, then you have to test each endpoint. They can either both diverge, both converge, or do one and the other. So let's try example 5. So again, I've done the ratio test for you here. So our ratio test, we got the limit being absolute value of x plus 1 divided by 2. So we want that expression to be less than 1. In other words, if we multiply by 2, since 2 is positive, we can just kind of multiply both sides by 2 and say that we want the absolute value of x plus 1 to be less than 2. Therefore, we want the expression x plus 1 to be between -2 and 2. And when you solve for that, you get x being between, when you subtract 1, you get x being between -3 and 1. Okay, so now you need to test both -3 and 1 into your series. Now when you go back into your series, notice you have that -1 to the nth. You do have to take that into account because remember with alternating series sometimes will converge, but their absolute value doesn't. So make sure you take that into account when you test your endpoints. So I'm going to test at x equals -3 first. And so you get -1 to the nth times, plug in -3 for x, so you're going to have a little extra step here. All right, and let's kind of reduce this down a little bit. So we get -1, hold on, sorry, my pen started messing up on me. So we have -1 to the nth times -3 plus 1 is -2 to the nth over 2 to the nth. Now, this can actually simplify because every single one of those terms is to the nth power. Then we can simply multiply them together. So -1 times -2 is 2. Then 2 divided by 2 is 1. So what you end up getting here is the series 1 to the nth. Not 1 over 1 to the nth, but 1 to the nth. So think about that. If you were to take the limit as n approaches infinity of 1 to the nth, and really 1 to the nth is just 1, I shouldn't have even written nth. If you take the limit of 1, you get 1, which isn't equal to 0, therefore diverges by nth term test. Okay, so that means -3 does not converge. Okay, so I'm going to erase the green really quickly so that I can go back and do 1. Okay, so now to test at x value of 1, let's go back into our series. And so we have -1 to the nth times 1 plus 1 to the nth over 2 to the nth. So that 1 plus 1 is just 2. And you see you have 2 to the nth over 2 to the nth, so that's just going to cancel out, leaving you with -1 to the nth. Now, 1 to the nth is 1, and that diverged, but also -1 to the nth. Don't be fooled by thinking alternating, oh, it's going to converge. But it's not -1 to the nth over n, it's -1 to the nth. And so what's going to happen is the limit's going to go back and forth between +1, -1, +1, -1. So therefore, this is not equal to anything. It diverges, or because it does not exist. Okay, so the limit does not exist due to oscillation. Therefore, diverges by term test. Okay, so both of our endpoints diverge here. So the interval of convergence would be -3 to 1 open endpoints. All right, final example. Find the interval of convergence for this. Again, ratio test has been done for us. So we have the absolute value of x being less than 1. So that means x is between -1 and 1. So we want to test those values. So at x equals -1, we have the series -1 to the nth over n squared. Now remember, if you take the absolute value of any series and that converges, then the original series converges absolutely. So if you think about the absolute value here, you get 1 over n squared, which is a convergent p-series, where p is equal to 2, which is greater than 1. You could even say a convergent alternating p-series, So that's pretty given. If a convergent p-series is alternating, then it will be convergent. All right, and then when we test at x equals 1, we've already discussed that. So 1 to the nth is 1 over n squared. So that's not alternating, but still convergent p-series. All right, so therefore our interval of convergence here will include both endpoints. So that's -1 to 1 with brackets. All right. So we have the radius of convergence is how far away from the center it can go, and then the interval of convergence where you have to test the endpoints if you get a finite radius. Okay, so that's power series. Now there's one final thing that we're going to look at, and that is looking at the properties of a function defined by a power series. Now, since a power series is a function, well, what do we do with functions in calculus? We take the derivatives or we take the integrals. So now that we have this new function, we're going to talk about taking the derivative or integral of the power series. And then we're going to talk about the interval of convergence of those. All right, sorry, this keeps popping up. So if the function given by that, the power series, has a radius of convergence that is greater than 0, then on the interval of convergence, f is, and notice, actually, it's not the interval of convergence, it's the open interval. So we're not considering the endpoints here. So on the open interval, f is going to be continuous, differentiable, and integrable. That means, in other words, I can take the derivative and I can take the integral of those. Again, if it has a radius of convergence that's greater than 0. All right, so we kind of define the derivative and integral, and all we're doing here is it's just really applying the power rule. So if f is defined here, if you were to take the derivative of that, then it's just power rule, so you would bring that n down in front, so that's where this n comes from here, and then you would make your n to the n minus 1. All right, so very, very simple there, and the a sub n and the x minus c will not be changing. All right, and then the same applies for the integral of f of x. Notice you have that plus c there, right? When you take the integral, you have a plus c. And so when you take an integral, you take your n to the n plus 1, and you also divide by that n plus 1. Okay, so same rules apply with this. It just kind of looks funky. All right, so this is quite important here. This is something that you need to memorize. Absolutely memorize. So the radius of convergence for the series obtained by differentiating or integrating a power series is the same. Now notice the radius of convergence is going to be the same. Okay. So if I'm going from -1 to 1, then the derivative or the integral will still be from -1 to 1. However, the interval of convergence, so that really what that means is the endpoints may differ. Okay, so if I was going from -1 to 1, let's look at example 4, like this one. Okay, and I was to take the derivative of that or the integral of that, it's still going to be from -1 to 1, but what may differ is how the endpoints converge. Okay, so that's what we're going to look at in this final example. All right, so and actually number 7, if you see, is the same exact function as number 4. So we don't have to do all of that work. We already know the radius of convergence and the interval of convergence from -1 to 1. Okay, so kind of make a note to yourself to see number 4. We're not going to do all the work here. All right, now first of all, before we find, so all we have to do, is to evaluate the derivative and the integral at the endpoints, because I know it's from -1 to 1. I just need to know what happens at those endpoints. So before I can do that, I had to come up with a series that represents the derivative and the integral. So that's the first step that we're going to do. So we have f of x defined as the series of x to the nth over n. So now when I take the derivative, again, it's going to be defined as a series. And so applying the power rule, the exponent n is going to come down times x to the n. When I take the derivative, that's going to be subtracting 1. The n in the denominator is just going to stay there. It's going to stay exactly the same. All right, but then you can clean that up because when I multiplied my x by n, those cancel out. So now the derivative of our function is defined as the series of x to the n minus 1. Okay, so now you need to test the endpoints. for this function. So we're going to test x equals -1 for our derivative function. So that's going to be the series of -1 to the n minus 1. Now, for the same reasons that we saw, I believe, in example 5, this is going to be divergent by the nth term test. Okay, so that is not going to be convergent. And then we want to test at x equals 1. And again, I know it seems tedious, but you do have to write all of this out. So 1 to the n minus 1 is just going to be 1. Therefore, that also diverges by nth term. Okay, so our interval of convergence for the derivative, if you notice in example 4, -1 was inclusive, but 1 was not. And that was dropped for the derivative. The derivative does not include either -1 or 1. So the interval convergence for the derivative is that. Okay? So then finally we need to find the integral of our function and find whether that converges or diverges at the endpoints. So the integral of our function is going to be the series. So we have x to the nth over n. So to take the integral, we would have x to the n plus 1 divided by n plus 1. Now that n in the denominator that was already sitting there in the original function is still going to be there. And then we're going to multiply by n plus 1. So if we clean that up a little bit, we get x to the n plus 1 divided by n squared plus n. All right, so now let's test those endpoints, -1 and 1 again. All right, so for -1, we would have -1 to the n plus 1 over n squared plus n. Okay, so this is alternating, and if you notice in the denominator, it looks like a p-series. So if you were to actually test the convergence or divergence of this, you would use a comparison series. So this converges by comparison to 1 over n squared, which is the convergent p-series. Okay. All right, so it converges at -1, and then also we want to test x equals +1, which I'm sure you can see where this is headed. So 1 to the n plus 1 is just 1 over n squared plus n, and then pretty much same thing as what we wrote above. So that also converges. All right, so the interval of convergence for the integral, that differs in that it picked up both endpoints. It didn't drop any. And actually, that's not going to always happen that way, but most of the time it does most of the time it happens that way, but not always. So that's what I kind of said in this last sentence. You are more likely to lose endpoints when differentiating and gain endpoints when you are integrating. Okay, most likely, not all the time. All right, so that is power series, finding the interval of convergence, radius of convergence, and the derivatives and integrals.